Okay guys, so today we are solving a beautiful Putnam 1979 problem. So, given n red points and n blue points in the plane, no free collinear, prove that we can draw n segments, each joining a red point to a blue point, such that no segments intersect. Awesome. So, first of all, what this problem statement even tells us? It means that whenever we have a plane, let's say this is our plane and we have some n, let's say 4 red points and let's say 4 blue points as well, we can connect those points using line segments in such a way that none of those line segments used to connect those points are gonna intersect. Yeah? Okay. So how are we supposed to prove it? Well, proving it by induction would be pretty damn difficult. like really. And honestly, I think it will be pretty impossible. I would like to use a nice thing. I'd like to use a nice trick, which is an algorithm. So if we were able to prove that there exists an algorithm that whenever given a set of points that are connected in a absolutely random way. So let's say this point is connected to this point, those two are connected, those two are connected, or maybe no, those two are connected and those two are connected. Yeah, so we have quite a few intersections right over there. Then this algorithm will be able to take those segments that cross each other and just uncross it in such a way that, well, still all of the points are gonna have a point made of theirs such that they will be connected to it. Yeah, so we will be at, let's say, this kind of a position of those segments in the plane. Yeah, so if we manage to prove that there is this kind of an algorithm, then we will be able to prove that our statement is true in general, because, well, whenever there will be a set of points in a position, we can just connect them randomly and just apply the algorithm. Boom, everything's awesome. Yeah, lovely. So how are we supposed to come up with an algorithm like that? Let's maybe consider a set of 4 points in total, so 2 points red and 2 blue points, yeah, something like this, and let's connect them right like, oh my god, like this. Well, we can kind of go on and interpret those line segments that connect those points to each other as diagonals of a quadrilateral whose vertices, or which vertices are gonna be the points, the 4 points that are connected by the intersecting line segments. And now what we can do is just go on and delete those diagonals from the image. We can just go on and also delete those sides of this quadrilateral that connect the monochromatic vertices, so vertices that are colored the same color. And as we can see, we're left with just 2 sets of points that are beautifully connected with each other with line segments that do not cross. And so, will this kind of an algorithm work in any way? I mean, in any position? So let's maybe try and apply this algorithm here to this example. Let's maybe first of all try and uncross those guys right over here, because why not? Then we will just oh no, we will have to uncross this. Oh man, this and this guy. Yeah, we will connect those two to each other and those two to each other, and actually it's quite lovely because it did manage to uncross all of the crossings in the plane, that, well, all the crossings that occurred in the plane earlier on. Awesome. So we see that this works, but how do we prove that this algorithm always works? Well, if an algorithm is to always work, it has to satisfy one crucial condition. It has to always come to an end. Its application has to always come to an end. This algorithm has to always end. What do I mean? Well, for example, if I have an algorithm that is an algorithm of me walking a mile, yeah? So I'm going to walk a mile, and I have like an n steps to make in order to, walk a mile. I know that this algorithm will stop eventually, because at every single step, the number of steps that I have left decreases. And I can't have negative steps left. I can only have 0 steps left. So I know that at some point, I will have 0 steps left to go, well, that mile. And this is a perfect thing, because I know that thus the algorithm will terminate at some point. And so I can use the same reasoning to prove that this algorithm will terminate too. And well, if it does terminate, if I find something that decreases at each time I iterate, I apply this algorithm, then well, I will know that I will be able to reach a state when all of the crossings are uncrossed. Awesome. So what is the thing that decreases? What is the thing that decreases? Maybe I will even write down this question. What decreases at each application? Well, one might say the number of crossings. It decreases, but it doesn't really. I mean, consider this kind of a case. We have, let's say, those 4 dots right over there, yeah, so those are connected like this, and we have a dot here, a dot there, and also a dot, oh man, a dot here and a dot there. And we have those connected like this. Well, if we were to apply our algorithm right now to this position, we see that all of the crossings are not going to be immediately resolved, and that's because after applying it, we will get those 2 lines, but now the new line here intersects with 2 line segments here and here. Well, not quite lovely. I mean, we still can apply the algorithm, of course. There's absolutely no problem in doing that, and we will still end up in a position where all the crossings are going to be uncrossed without the problem. However, we see that the number of intersections does not necessarily decrease at every single step. It actually can increase, because we had only a 1 intersection, and now we have 2 intersections. So what is something of a real number that decreases and that cannot go to 0? Something that decreases at every single step. Well, there is one thing, and it is the lengths. You see, when I said that whenever we had this kind of a position of our points, and they are connected in this way with just line segments, then we could treat those segments as diagonals. Yeah, I actually gave you a hint to think about those green lines as diagonals. You see, diagonals are always gonna be longer than sides. Yeah, it should make sense. And so now when I deleted those diagonals and instead I drew sides as my line segments that connect those points, those sides are shorter. Those lines are shorter than the previous lines I had, the previous line segments I had. And so we see that what decreases at every single step is the summed up length of all of the line segments. It decreases. So we found something that does decrease, and something that just cannot go down to 0. So we know that eventually something that cannot go below 0. So we know that our algorithm will eventually end. So once again, what decreases at each application? I'm gonna quickly erase it, and I can say the total length of line segments. Lovely. Okay, so once again, what did we do here? We're supposed to give the red points and blue points, connect those using line segments, and then prove that we could connect those using those line segments in such a way that none of those line segments would cross each other. And we came up with an algorithm that whenever given a absolutely random state of a plane and some double n vertices, double n points that are connected with each other, can uncross all of the crossings of those line segments, and we prove that this algorithm terminates eventually, because what decreases at every single application of this algorithm is the sum of all of the lengths of the line segments we use to connect those points to each other. And so we know that it terminates, and so we know that whenever this algorithm is applied to a general position of some kind of a plane, it will eventually get us to the point where non-crossings are there in the plane anymore. Awesome. So that will be all for this problem. I hope you enjoyed it, and see you in the next one. Bye.